So in this session, I will be talking about building multi-level models, how to do that, sequencing about this, and assessing model fit. Both are very important pieces, so pay close attention. So before you start building your multi-level model, there are a couple of things that you need to do, and those are very similar to what you do when running a regression. So you're doing univariates, bivariates, and then you move on to multivariable models. So the first step is to carefully examine the univariate frequency distributions of each variable that you might enter into the model. So you check the quality of the data. You check also the quantity and the distribution. This is especially important to have an understanding about your cluster sizes, number of clusters and cluster sizes. We talked a little bit about power and distributions. You want to identify outliers just as you would do in any other analysis, and then you want to assess the need for variable transformations. In multi-level models, equally to regression models, there are no distributional assumptions about your predictors. So your predictors can be binary, they can be pretty much anything, but you have to be able to interpret them. However, if you have major outliers or major spread, let's say you have a distribution that has a really, really high skew and therefore really long tail, it can bias your estimation because there's just sparsity of data at a certain part of um, the spectrum, and so you might want to consider transformations. After you've explored your univariates, you want to explore your bivariate relationships. And to do that, if you have a multi-level model, it means that you will have to run your bivariates in a multi-level model. What does that mean? So you have your unconditional model, which models the structure of the data, accounting for the clustering. And then you want to run bivariate models, meaning you will enter each predictor on its own and see how the models are doing. I would strongly suggest to model level 1 predictors with a random effect um, and to see what's going on there. So that gives you an idea about what are relationships, what's the size of the relationship, what's the significance level, and it's up to you. So depending on what you'd usually do with a regression, you could set a cut point for p-values for inclusion into a multivariable model. Now, it's not usually my approach because I firmly believe that you should build your models on theory only. But we also know that sometimes we are running into power issues, and then you want to have some parsimony in your model. So that could be a reason why, let's say, you estimate your bivariate relationships, and if those are too small, or the p-value is, let's say, above zero point 0.1, then you might want to exclude that relationship, that predictor from your final modeling process. You also want to look across levels, so looking at different groups, especially if you have large clusters, running some ordinal least square regressions for each of your groups or clusters allows you to find some outliers in groups. Looking at means and standard deviations per group, looking at those distributions is another way of looking at those. And you could get implausible results if you have small sample sizes, unusual characteristics of the group, or coding errors. So these are all good measures to get to know your data, and this is why I've highlighted this in red. You need to get to know your multi-level data really well. So this is something that you also should be doing for regression data, but now there's this added level of the clustering that really has major impact on modeling. And if you know your data well, that means that you can then later on way better interpret what you find, and B, make much better decisions if there's things that are not going well. So when it comes then to model building, you've done your univariates, your bivariates, you looked at all those things that I just talked about. Then we're going back to how are we going to build the model. There's two general approaches, and one thing that is important is to answer the question, what is your focal relationship? So in your research question, what is the focal relationship? And I want you to really think about this, and we will come back to that and it's something that you should be able to talk about. And a focal relationship is usually what is a key predictor, a key set of predictors that I'm interested in regarding the outcome. So that could be what neighborhood characteristics influence physical activity. And in that case, then if I ask the question on what level in your model is the predictor of your focal relationship, or in this case, your predictors, I would say on the neighborhood level. So I want you to take the time and think about your research question. What is your focal relationship? And what level is your predictor on? Because that will actually influence how you will be modeling things. So for the longest time, and this is kind of the tradition I was educated in, approach one was the go-to approach for me. And so let me talk you through this approach. Approach one is that your first model is the unconditional model, so no predictors, and you would run that model and calculate your ICC. Then you would add your level one predictors. And after that, you would be adding your level two predictors into the intercept. That's what we've done so far. Those are direct effects of level two predictors. And then you would add level two predictors modeling your slopes, and those are cross-level interactions. So this is exactly what we've been doing in our most recent class session and what you've been exposed there. So the cross-level interactions come last, but the sequencing is unconditional model, level one predictors, level two predictors, and then cross-level interactions. And then I started working with people who come from different traditions, and especially Hannah Cooper, some of you know her, who really is interested in neighborhood effects. And the individual level predictors are really more of control variables in her model. So um, in her approach, her focal relationship is about neighborhoods influencing outcomes, and those could be substance use, those could actually be HIV infections, those can be all kinds of things, but it's about what's going on in the neighborhood that influences those outcomes. And so in those cases, if your focal relationship has a key predictor or predictors on level two, you want to change your sequencing here. And so we're still starting with the unconditional model. There's no way around this. Don't ever skip it. Calculate your ICC, and then you would enter your level two predictors first. So you would look at your focal relationship first, the way you would do it in approach one if your focal relationship is between level one variables and the outcome. And after having the level two predictors in there, then you add the level one predictors. And then as a fourth step is when you will be adding your cross-level interactions. So the second step is really the one that is driven by your focal relationship. You first want to look at an unadjusted relationship between your key predictor or predictors and your outcome. So I've talked about the general major steps in terms of entering predictors, but let's take a little step backwards, building the model again. And so the most important thing is that theory should suggest your predictors. And this is important in terms of what to include, but also in terms of being really aware of what you cannot include, but what your theory suggests might be other key players, because what that means is that you're misspecifying your model. And you will have to think about this. What are the implications of that? So, but let's assume you have the data. So, should a predictor be included? Yes or no? And again, you have theory, and then you've looked at your data and your univariates and your bivariates, and those will give you an indication. How should the predictor be specified? If we're talking about level one predictors, we have some choices to make. Is it going to be just a random effect? Is it going to be a fixed effect? Or do we have a non-randomly varying effect? Which means, do we know that there's something going on level two, like a cross-level interaction, that we really need to put in? And that's really important. So sometimes we already know that there is something else going on the higher level that influences our level one predictor to outcome relationship. In general, Raudenbush and Breich suggest to add one predictor at a time, and you might want to do this especially when you're just doing your modeling. However, it might make sense to add all predictors at one level at once or in meaningful batches. So this is similar to using batches of variables in a regression, something we might call a block regression. Um, it might actually make sense to add them individually, but then report them in those batches. Um, that depends on how well your bivariates have gone. If they're very solid, then it's much easier to add things in batches. But if your bivariates are already a little problematic, I would want to go step by step. And as I already said, that your best predictors might have already been identified through preliminary OLS analyses and bivariate analyses. People have different approaches. Some like to probe a little bit more with the models, running more different models. I like to really go theory-based and then backtrack if the data don't do well with the model. So cross-level interaction effects are usually your last part. And for many of the models that we run, those are still the most exploratory part because the literature is still sparse on interaction effects between levels. The literature is expanding, and if you're going into some of the areas where there is a longer history of those models, for example, looking at neighborhood effects, then you might find some suggestions in the literature that make it a stronger confirmatory model, meaning you have a stronger theoretical and empirical background to justify including a cross-level interaction effect, but many times we don't have that. So many times we're just going to do these models towards the end. You're like, let me look, I have some hunches, there are some indications in the literature, but it's not too strong. I also know that there's some people who just do these for good measure. That's kind of the epi approach. If you have variables, throw in interaction effects. I'm not a big fan of that because the models are quite different from a regression model. So you're putting much more computational efforts into this. And again, theory-driven modeling allows you to draw stronger conclusions. So I would not suggest this. Another recommendation is don't add too many. You want to be somewhat parsimonious because you're splitting your effects into multiple components and your power is much lower with interaction terms in general. But now that if you have a cross-level interaction, you have no variance within a group in your level 2 predictor. So that adds to the power dilemma. So power is even lower when we're talking about a cross-level interaction effect compared to a within level interaction effect the way it is in standard regression. One thing you will learn when you start running multi-level models, you might not always get an answer. We call this convergence. Convergence means we get an answer. That means that the estimation algorithms find a solution that that they're confident in, that it's a solid solution, but sometimes there is no way to find a solution. And then we have non-convergence, and that doesn't happen OLS regression because of the math. You can always find an answer. That doesn't mean that that answer is a good one, but there is no barrier, there is no roadblock that says, oops, no, you can't go beyond this because your data quality is not good enough or your model is too far misspecified for these data. So I want to talk about two estimation algorithms, and those are for continuous outcomes. We'll talk about others when we move on to non-continuous outcomes. So what used to be the standard was maximum likelihood estimation, and it is exactly what it sounds like. We're looking for the answer that has the maximum likelihood, the most likely solution for the data, for the model given the data. You shouldn't use this if you have small level 2 sample sizes, so fewer than 30. It allows for model comparison for nested models. I will talk about those later with different fixed and or random effects. And the more predictors you have, the more biased is the level 1 variance. It underestimates the level 1 error variance, and therefore it's producing artificially small confidence intervals. I will move on to the next slide because maximum likelihood estimation is still used a lot, but I wouldn't necessarily recommend it. So after maximum likelihood, restricted maximum likelihood algorithms were developed. And don't ask me about the specifics in math, they're very complicated. But it is the default setting in HLM7, which means Raudenbush and Breich think this is the way to go. It is the standard estimation methods for two-level models. If you really want to run a maximum likelihood estimation HLM7, you have to go to other settings and estimation settings and click full maximum likelihood. And that's compared to restricted maximum likelihood estimation. If you're running REML or restricted maximum likelihood, it allows for comparing model fit statistically only when you have two models that have the same fixed effects but differ in random effects. So you could run a model where you have a random effect and take it out for the next model, and you could see if the more parsimonious model, um, if the difference that you're getting, if it's significant or it's not. I'm not the biggest fan of those model comparisons, but once in a while people ask for them. If you build your models on theory, that should not really be a major concern. So let's talk model fit. And there are multiple components that you want to look at and that you want to report. Some of those are similar to what happens in regression, and some of those are a little bit more complex. So first of all, we're going to look at the fixed effects. Those are our betas or gammas, and those are just testing if the effect itself is statistically significantly different from zero. And those are t-tests, and that's very similar to what we see in a regression. But then we have the random effects, and the random effects also have tests associated to them. In HLM7, you have a chi-square test. Um, and in SAS, for example, is a wald test. I'm pretty sure that Stata does also conduct a wald test. That tells you if the random effect, if the variance that is not accounted for is statistically significantly different from zero. Now, HLM7 does not give you a p-value for the chi-squared for the level 1 variance, and the reason is that we always assume that there will be some leftover noise on the individual level, and therefore it's not really meaningful to see if this is significantly different from zero or not. So beyond the individual predictors and random effects, we also want to look at overall model fit. The standard overall model fit indicator is the deviance statistics, also called the -2 log likelihood, because you take the likelihood and then take the logarithm and multiply it by -2. So that's literally what this means. And it measures how badly the model fits compared to the ideal model. So the closer to zero is better. Smaller deviance from ideal fit is what you want to see. And it allows you for statistical significance test for nested model if the ML algorithm was used, and I will show you how to do this shortly. But you can only use this if the same data were used to estimate both and one model is nested within the other. Let me talk about this in general, and this is important. So when you create a analytical data set, you might want to make sure that you deal with missing data. Because the problem is, let's say you run your unconditional model, which means all the outcome data is there and all the data will be modeled. But let's say then you're adding age as a predictor and you have some missing data, which then means that that data set will actually be smaller for that analysis. And then the models are not comparable anymore. So you will have to look at your missing data and have to make decisions about multiple imputations and different things like that beforehand, because you really don't want to compare apples and oranges. Let's say you actually will have, let's say you're using listwise deletion and you're missing 5% of the data. So you're running the final model on 5% fewer people than the unconditional model. Then what does that mean for any comparison between models? On this slide, we're gonna skip over this right now because I will get back to the last. Beyond the deviance, there are two generally used overall criteria that are used for overall model fit, and one is the AIC and one is the BIC. And those two all build on the deviance, but adjust on different things. So the AIC can be calculated as the deviance plus 2 times P, where P is the number of parameters. So remember, larger is worse, so you get penalized for having more predictors in your model and more random effects. So this is aiming for parsimony in your model. The BIC goes a step further. It includes not only P, so how complex is your model, but it also includes the sample size of your for your study. And so there's two things that play a role in there, because if you have a larger sample size, you get away with more predictors. But so for HLM7, it doesn't spit those out for you, but SAS and most other software packages will spit them out for you. So I want to use the example from last week's class session to talk about model comparison. So you ran 4 models. The first one was the unconditional model. The second model had a individual level predictor of fear in it only. The third model had only a neighborhood predictor in it. And then the fourth model had both direct effects and an interaction effect in it. So I'm going to talk about those 4 models. So for your convenience, and you can look at the HLM output, you will see that these are the numbers from the output from those 4 models that you ran in the last in-class exercise. So I just copy and pasted the deviance. It's all the way at the bottom of the output. The number of parameters estimated is also there. And then the level 1 sample size, the total sample size in this case actually. And I want you to stop when I stop talking at this slide. So I'm going to say stop. And I want you to take your calculators or a spreadsheet preferably and calculate the AIC and the BIC. The answers will be on the next slide, so I really don't want you to look. So I'm going to give you some pause, so time to, I'm going to pause to give you some time to click and stop this. Did you stop it? So this slide shows you the answers for the AICs and the BICs, and I hope you got the right answers. They should always be larger than the deviance because you're actually adding positive numbers to them. But you will see that in this case, you can now look at the 4 numbers, and what you see is actually for the deviance, the more complex model fit the data better. And when you look at AIC, you see exactly the same pattern. The numbers go down in terms of models 1, 2, 3, 4. Remember, 2 is individual level predictor, 3 is only level 2 predictor. And then interestingly enough, for the BIC, the smallest number is for model 3. Model 4 is only slightly larger, but we will look at that if that is statistically significantly different. So here are the model equations again, and this is really just copy and pasting the earlier slide. What I will be doing next, I will be looking at nesting in those models, so bear with me. So 2 models are nested, or better, model A is nested in model B if I can add something to model A and get to model B. Only adding. So when we look at this diagram, I wrote the equation out. So model 1 is the unconditional model. It's the simplest model we can run for a multi-level model. And that model is nested in any subsequent model. So model 1 is nested in model 2. We're adding fear to it. And we're adding a random effect of fear to it. So both of these components are in there. Model 1 is also nested in model 3. And we can expand model 1 by adding gamma 0, 1 times the mean problem score of the neighborhood to it. Model 1 is also nested in model 4. Now, model 2 and model 3 are not nested in each other. They have different predictors, and I can only get from model 2 to model 3 by taking some things out and adding some other things. However, model 3 is nested in model 4 because we can add the direct effect of fear and the cross-level interaction. And model 2 is also nested in model 4 because now we're adding the mean problem score and the cross-level interaction between the two predictors. So the diagram here shows how the models are nested. Now, let's assume we ran these with maximum likelihood estimation. We can then calculate if the difference between the models is statistically significant. So how do we do this? There are three steps. The first one is you calculate the difference between the two models in the deviance. The more complex model should always fit better because you're modeling some of the variance, so there should be less unmodeled variance. Then we calculate the difference in degrees of freedom, which is the difference in parameter estimates. And then we look up the chi-squared and see if it's greater than the necessary cut point for an alpha of 0.05. And we will need a table for that, but those are either in statistics books or easily accessible online. So let me walk you through this. So I've copy and pasted the front piece from the table you've used earlier to calculate the AIC and the BIC so that we have the numbers readily there that we need. And then we're looking, so model 1's nested in model 2, so you have to calculate negative 1038.37 minus or plus negative 1012.39, and that gets you, if you use a calculator correctly or Excel, 25.98. So that's the difference in deviance. The difference in parameter, which is the same as the difference in degrees of freedom that you have, is 3 because we're going from 3 to 6. So 6 minus 3 equals 3. I'm going to walk through one more example that's from model 3 to 4. It's the very last one. 987.91 minus 964.92, so 22.99. And we're going from 4 to 8, which means there is a difference in 4 parameters. So those numbers are the ones that we now need to look things up. So let's look at that first case, 25.98, and remember 3. So 26 and 3. Let's look at it. So as I just mentioned earlier, you can just go and Google a chi-square distribution table and these things pop up. Here's one that I found conveniently using Google. And given that these all contain the same numbers, you don't really have to be concerned. These are also in the back of your standard statistic books. So I've highlighted the column that we're interested in, and that's the alpha for 0.05. And you might already know, and if not, it's something that you might want to keep kind of somewhere handy. 3.841 is for 1 degree of freedom. If you're doing structural equation modeling, you will need that as well. That's for your modification indices. But what we're looking at right now is the chi-square cut point for 1 degree of freedom is 3.84. For 2 is about 6. For 3 is about 7.8. We just had 3 comparing model 1 to 2, and so we need the row with a 3 here, and we have a deviance of 26. That's way larger than the 7.8, which means there's a significant improvement in your model if you're going from model 1 to 2. So model 2 fit the data better than model 1, and statistically significantly so. And that's how you would go through this table. I'm going to show you the overview of our nested model diagram in the next slide. So here I've now taken out the equations and I've added the numbers from the table and then looking things up, and actually I think I put it in a calculator. That's why we're getting things at 0.01, but you could also just look at different columns. So when you look at this, all of these models are, the more complex models are statistically significantly better fitting to the data than the simpler model. So model 2 is better than 1, model 4 is better than 1, model 3 better than 1, but model 4 is also better than model 3. Remember, that's where we had kind of the BIC for model 3 was slightly smaller than for model 4. And then we also have model 4 is definitely better than model 2. So overall, model 4 is the best fitting model of those that we tested in the sequence for our data. And this is important. We never talk about the data fitting the model because the data are. They are what they are. It's a beautiful use of a tautology. You don't fudge with the data. We're trying, not fudging, but we're testing different models to fit to the data that we have. So there is one other model fit assessment that you can do, and there's actually two that I will talk about, but one that I will ask you to do for the models that you have throughout the class and also when you publish, and that's the predictive ability of the model. So the equivalent of this is the R squared in regression. Now, people have tried to come up with an equivalent. The problem is in regression, as you probably know, if you add more predictors, your R squared gets larger. So adding more predictors means that you're explaining more of your variance. Now, given that multi-level models function differently, it can actually happen that you add predictors and your R squared goes down. So people don't like to use that. And there's actually, it's kind of a hobby of statisticians coming up with different ways of looking at that. To date, I have not seen one that has been established to the point that we should report it. So there's not one overall number. But given that we have different variance components in our models, we can calculate a proportion reduction variance. And you've done that actually in the first session, not in the first session, but in the last exercise, not in the last, but the second to last exercise when I asked you to compute this and I gave you just the formula. So here's the formula again, and it's really just you're taking one type of variance across models. So let's say you're taking your tau 0, 0, which is the variance that's associated with your intercept on level 2, and you have a baseline model, which should be the model where this number shows up first, which in that case would be the unconditional model, and then any kind of later model, and you want to see how much is that reduction. So you subtract the later model's variance from the earlier and divide it by the initial variance. So that's the proportional reduction. And that's literally what it means. By how much was the variance reduced and how much is that out of the original variance. So you get a percentage between 0 and 100, and that gives you an idea of how much of that variance has been explained in that model. Please note that we will calculate those for the level 2 variances and the level 1 variances. And because things interact, sometimes those actually get larger in between. They will never get larger from your initial model, your baseline model, but they can actually go up and down because the variances all interact. And so you might see a reduction in your level 2 variance when you're adding level 2 predictors, but then your level 1 variance might go up at the same time. And we'll talk about some of this more, but it's in the nature of the data. So here's just a slide where I copy and pasted the calculations for the proportional reduction of variance for the exercise, and this was last week's or last week's, that depends on when you're watching this video. This was session 3 in the classroom exercise, and here we only had a level 1 variance. We always have the Rij or the sigma squared associated with it, and we had a random intercept. So we had a tau 0, 0. So those are the two that we calculated, and what we saw here is that the final model actually accounted for 71% of the level 2 variance and 8.4% of the level 1 variance. Lastly, I want to mention another way of looking at predictive ability, and this is an R squared that has been developed. I'm blanking on the name right now, but it's in some of the recommendations to report. And so this is a proportional reduction prediction error. And you calculate that by looking at your level 1 random effect plus your level 2 random variance. You divide that for the final model by the initial model and then subtract it from 1. Now, that formula has been used for a while, but the problem is it only works if you only have a random intercept. As soon as you have a random slope, you can't use that formula anymore. And there are some formulas out there, but it gets mighty complicated. A, locating them, and B, calculating those. So while this is recommended by some people, it's rarely used. However, if you have a model where you only have a random intercept, it could be one additional number you can report. So this is it for model building and assessing model fit. Right now, we will come back to model building and somewhat to fit throughout the class, but this is a solid base of information.